pendulums are things that show simple harmonic motion, sometimes abbreviated SHM. If we have a pendulum, maybe we have an object suspended from the ceiling here. Alright, if we pull it back to here, and we let it go, it's going to go past this, probably to over here somewhere. And then kind of go back and forth and swing like that. Okay? In a perfect world with no energy loss, if we have a 100% efficient pendulum, it would actually just keep oscillating back and forth forever. But most of our pendulums have air resistance and all that sort of thing involved. So any pendulum we create will eventually stop, unless we have it synced up with like the tides and crazy stuff. There are interesting things going on at science museums and whatnot. But most pendulums we'll just put together in our spare time. That's what I do in my spare time. Will eventually come to a stop. But a perfect world theoretical pendulum will just keep going forever in a predictable way. Now, we can talk about its period, t, and it's a fairly simple formula. The period of the pendulum is 2 pi times the square root of L over the absolute value of gravity. Okay, L is just the length of the pendulum. That would be L, how long the pendulum is. And that's a pretty simple idea. And it's a pretty simple formula. And you will have to do a handful of problems using this, but this is easy. It's just an extra thing for you to have to remember. There haven't been a whole lot of new formulas in this chapter, really. It's just been remembering to do our old formulas still, which is really good practice for the midterm, which is coming up before you realize it. Okay, so that's how pendulums work. If we want to talk about the time or the period of a pendulum, 2 pi times the square root of L over absolute value of G. Sometimes you may say, here's a pendulum on the moon. Here's the period, here's the length, what's gravity? And so you can solve for gravity using this formula too. So that's kind of a neat thing. But that's basically it. So you have a couple of formulas, a couple of problems to do after this. But I have a feeling your quiz will have kept you mostly busy. Okay. Next, something called simple harmonic motion. Simple harmonic motion is basically just any sort of motion where there's an oscillation. Maybe a spring where we have a weight and we pull it down and it goes, maybe it goes down to here and it goes back up to here and it just, goes back and forth. That's harmonic motion, where it goes from equilibrium above and below, over and over. That's what simple harmonic motion is. Simple harmonic motion has two things: period, which we've talked about before. That's the amount of time, basically, the amount of time needed to make a full circuit. And it has amplitude, which is a term you may see again. Amplitude is just how big the motion is, how far from the equilibrium point. Or so maybe a better way would be to say distance from the equilibrium point, or from the rest point. Okay, that's just what simple harmonic motion is. That's what period and amplitude are. There is something called Hooke's law. and I'm just going to mention this because I need to. Hooke's law talks about, well, it's a formula. It's F equals negative kx, where x is just displacement. That's how far. Hooke's law talks about springs. There are certain springs that are called like Hookean, that they follow this relationship. X is displacement from equilibrium. Basically, it's amplitude, how far you've pulled the spring from where it normally goes. K is something called the spring constant. It's actually measured in Newton meters, which is weird. And then F is just the force. Don't need to memorize this. For our purposes right now, just know that Hooke's law has something to do with springs. Now, an extension of Hooke's law that has to do with a mass on a spring says that the period of the simple harmonic motion of a mass on a spring, if you pull it down and let it go, is equal to 2 pi times the square root of the mass over the spring constant. And note the spring constant is under the square root. So if I give you a problem about a spring with a mass on it, and I give you the mass and the spring constant, you can find the period, or vice versa. Now, I guess let me do some algebra for you guys, in case you can't figure it out. So if we want to solve for mass here, it would be what? The square root of m over k equals, my pen's being screwy, equals t over 2 pi. Okay, so then we have to square both sides, so it would be m over k equals t squared over 2 pi squared. Okay, then we could cross multiply this, and we'll get t squared k equals m times 2 pi squared. And then that should be pretty easy to solve for either k or for m. You just divide both sides. But I know some of you act like you've never taken Algebra 1 before, so here's a little bit of hand-holding for you. You should be able to solve this equation for k or m now. So a wave, basically, and we know what a wave looks like. Most of you are at least in trig, so a wave looks something like this. Okay, that would be approximately a sine wave. Yeah, there are two main things, very basic level things we can talk about with a wave. We can talk about frequency, and we can also talk about period. And we've talked about period before. Period in physics is generally represented by a t. Frequency is going to be represented by a lowercase f. And so the relationship between frequency and period is this. F equals 1 over t. And the unit for frequency is hertz. Which is abbreviated to capital H lowercase z. Hertz. A hertz is 1 vibration per second. See, this is per second divided by second. So 1 hertz is a vibration per second. So that's our big thing. So looking at this, you see here's a wave that I just harvested from the internet because that's how I roll. There are a couple other things we can talk about. One is wavelength, which you can see here. I'm not sure how well you can see that, but this is a lambda. It kind of looks like a upside down Y. Let me see if I make that more clear. so lambda, and that stands for wavelength, and that is the distance, basically the length of the wave. Is a highly descriptive name. Generally, it's measured between points like this. These points are high points, and they're called crests. But it can really be measured from any point that you can identify pretty easily. Down here, we could do these, the low points, and this would be the same distance, the same wavelength. These are called troughs. Okay, so we got crests and troughs. We could measure from here to here. It would be the same length. That's wavelength. That's what it is. Okay, there's something else it's talking about here, and that is amplitude. And that's given by, in this picture, it's given by, it looks like a Y. That might be like a lowercase gamma or something. We're not too worried about the notation for amplitude. I don't think we're going to be doing any calculations that involve amplitude. You just need to know what it is. And amplitude, as you can see here, is just the maximum displacement of a wave from its equilibrium point. It's basically how far away from the axis, if you can think about this is the axis, how far away from the axis the wave ever gets. That's amplitude. So those are easy ideas. Wavelengths is obvious. Remember what frequency and period are. Crests and troughs are obvious. So that's pretty easy stuff. Okay. Sometimes we can talk about the velocity of a wave, and there are two different ways that you'll see it expressed. A simple way to think about it, and hopefully this makes sense. If we do wavelength over time, that's basically distance over time, so that's one way that you can talk about a wave's velocity. But divided by time, well, remember how frequency equals 1 over period, divided by period? So we can also write V equals lambda f. So the wavelength times the frequency can be the velocity of a wave. And so that's a pretty easy thing. The only problems that you're going to do in this section are going to be ones that use either this or this formula, or maybe some combination of the two, or I guess this one too. But that's all easy stuff. I mean, it can't get much more elementary than that. So what you'll do is you'll define some terms, because there are a lot of terms in this chapter. There's lots of stuff you need to know. And then try to answer some questions. And so you may need to read certain passages from the book, ask questions about it, get help, talk about it, whatever. Can't be too mad at me, because I don't really like to lean on the textbook too much. But this is just one of those things where what we normally do with kind of the problems and examples and whatnot just doesn't really work for this content. So that's the drill for today.